Hello there, and welcome to your introduction to COBOL. No matter what brought you here, we're glad to see you and hope that you enjoy all that went into creating these videos. First things first, what is COBOL? Well, whenever there's an acronym, I like to start there. And COBOL is an acronym for Common Business-Oriented Language. That's a big tell right there, right in the name. This is a business language. Compared with other more general purpose languages, COBOL was designed around data processing, specifically data processing with incredibly high accuracy, extreme efficiency, and ease of reading and writing. COBOL has indeed been around for over 60 years as of this recording, and surprise, surprise, the fundamentals of business, being able to process very large amounts of data accurately and efficiently, continue to be important. So all of the transactions that happen when you're using a credit card, visiting a store, or doing pretty much anything with a bank, there's a good chance some COBOL code got executed somewhere in there. In fact, every day about $3 trillion in finance gets handled by COBOL. So let's just make sure we're clear here. COBOL pretty much runs the world. It has been kept up to date to support new requirements throughout the years, and 1.5 billion lines of new code are written every year. Suffice to say, learning this language will give you a very valuable set of skills. In this course, you're going to be working with Enterprise COBOL, which is an implementation written specifically to run on IBM Z mainframes. The banks, insurance agencies, energy companies, retail chains that depend on COBOL to run their extremely important transactions, guess what? A whole lot of them also depend on IBM Z mainframes to ensure their applications can keep up with the demand 24/7. Learning Enterprise COBOL says, I want to work on the most important code, running on the most important systems, running the types of things that, no exaggeration at all, the world depends on. That's a pretty bold statement, and I have no problem at all saying it because it's the truth. You might be thinking, COBOL on the mainframe. Am I going to need punch cards and a tie to get through this? Well, first of all, no. You'll be happy to know that we're going to be teaching all this with Visual Studio Code, which as of right now is the most popular editor used worldwide. Visual Studio Code, or VSCode for short, supports something called Language Server Protocol, which simply put, makes it able to support a very large number of languages and environments. So the things you'd expect to be there, like code completion, workspace symbols, hover text, references, and diagnostics, can all be supported without it having to be specifically written into VS Code itself. It gains functionality through extensions, which use the Language Server Protocol, or LSP. We're going to use extensions for VS Code that give us all the goodness for COBOL, as well as allowing us to connect to a real live mainframe system. So after you download and install VS Code, hop into the Extensions Marketplace and search for IBM Z Open Editor and hit the Install button. While that's installing, do the same for Zoe Explorer, Z-O-W-E. That's the simple version of things. For more detailed instructions on installing the extensions, visit the book version for the full details and screenshots. Couple of basics. Once you're in, you'll also notice these vertical lines. Very important for COBOL. These are the margins. Those margins segment each line of COBOL code into its various parts, which we'll get into later on. Just know that it's easier to see whether your text is starting right next to a line than it is to count empty spaces. So lines, good. Also, if you hover your mouse over some fields, a little pop-up box will appear showing you additional information. Just know that this will come in really handy when you really start hacking away at COBOL code later on. And you may also notice that some words get displayed differently than others. That's all part of syntax highlighting. It just makes things a little bit easier to understand at a glance. And this bar across the top, that's the breadcrumb view. It shows information about what line you're currently at. Click on any element in that breadcrumb trail and it will highlight the block of text for that element. It'll also show you a little outline view of the code over here. Lastly, down at the bottom of your screen, there should be a panel with a Problems section. And if it's not there, go up to View and select Problems from the editor menu. You can click on the problems it has found and it will jump right to those in the code. It will find basic logical errors without you having to run or test your code. It just knows about those problems ahead of time. So you'll definitely want to fix those as they come up. Got all that? I'd say you're ready to dive into some actual COBOL. So let's go. COBOL is an English-like computer language. It's that way by design, meaning it's fairly easy to read, understand, and maintain. Compared with other programming languages, you'll find that each line of code is pretty transparent about what it's trying to do. That's often the first thing people notice about COBOL, that what it's trying to do is very easy to figure out, and you don't have to spend a whole lot of time tracing through code to make sense of it all. That's thanks in part to COBOL being standardized. So the way that a COBOL implementation should be approached is all described in great detail in that standardization. Now, COBOL has gone through several revisions over the years, so you do need to keep in mind which particular standard you're working with, particularly when you're working with code outside of this course. But it mostly comes down to the addition of a few new features, better support, and small tweaks to fix problems. COBOL, written specifically for the IBM Z mainframe operating system ZOS, is said to be Enterprise COBOL. The code you'll see here in this course is all Enterprise COBOL, and it all gets compiled and executed differently than COBOL you might be writing for other platforms. But it is also able to take advantage of hardware and operating system features unavailable anywhere else. So it still follows the current COBOL standardization, but it's written with enterprise systems in mind. Let's take a look at some of the basic COBOL syntax at a high level so you can get a better feel for the COBOL standard. Right up front, one of the key aspects of COBOL, some languages use spaces, some use tabs. COBOL is column dependent, meaning it looks at a line of code and expects certain things to be at certain positions in that line. Specifically, it's looking in 5 key areas of a 72-character line, and those look like this. The first section, columns 1 through 6, are the sequence number area. Sometimes these are blank, other times we use them to provide context to a series of statements. The next section is the indicator area, and it's a multi-purpose area. If we're going to leave a comment, an asterisk, a star, goes in here, or if we're continuing a previous line, it'll be a dash or a hyphen. It can also be a D for a debugging line, or a slash for source code listing formatting. Don't worry about all that just yet. We'll show you how and why you'll use those later on. Just remember, it's column 7 and it's 1 character. Next, we've got the A area, which goes from columns 8 to 11. In here, you'll find divisions, sections, paragraphs, level indicators, and other elements that give COBOL programs their structure. Right next to it, in columns 12 through 72, is the B area. This is where you put the actual statements, sentences, and clauses, the things that make a COBOL program, perform calculations, and do stuff. Then, last but not least, the identification area, running from columns 73 to 80. Well, the compiler might consider at least because it actually ignores it, so it doesn't consider it at all. It's actually an area the programmer can use for any purpose, so it's often just left blank. Now, when you're writing in a programming language, there are certain words we have to be careful of. Words like data, end, file, if, ready, set, until. Those are COBOL reserved words, and when the COBOL compiler sees those words, it thinks we're telling it to do something very specific. So we shouldn't say ready unless we mean what the compiler thinks it means. A full list of reserved words is available at the link in your guide. In the next video, we're going to talk about how all this fits together in the program structure. Let's talk structure. COBOL has a hierarchy structure, meaning that it's got things within other things. That's part of what gives it its structure. The biggest things in a COBOL program are divisions, and within those divisions there are sections. And within those sections you'll find paragraphs. Those paragraphs contain sentences, and sentences have statements. Let's start at the statement and work our way back out. A statement is a single directive, usually starting with one of those reserved words we just talked about. So something like add, divide, move, compute. Those statements go into sentences. Just like a spoken sentence can reveal many pieces of information, a COBOL sentence can contain one or more statements. It's just a nice way of placing a bunch of statements together into a logical container. So here is a sentence made up of statements, and you can see that at the end there's a period. That period is an implicit scope terminator. It says all the previous statements that have not yet ended are declared as finished. You can also terminate a scope of a statement using what's known as an explicit scope terminator, like if you started with an if statement and you end with an end if. Then you don't need to specify that you're done with a period. Either way works, and you'll see both used throughout this course. So that's sentences. And what do sentences go into? Well, generally paragraphs. Paragraphs are user-defined, written by you to give your program structure. Generally, a paragraph represents a specific action made up of smaller steps. So if it's something that might get called several times throughout your program, like applying interest or prompting the user for a series of input, that would go into a paragraph. That way, you can call that paragraph by its name from elsewhere in the program. Paragraphs go into sections, and there are all sorts of sections. They can have user-defined or predefined names, so they can be used to give your program structure or to make sure certain information is where it needs to be for things to run correctly. And then there's divisions. And there are 4 COBOL divisions, and we can cover all those right now. First is the identification division, which is where you'd put the name of your program, who wrote it, when it was written, how it should be used, all that helpful information. Then there's the environment division. There are 2 major sections here. One lets you set the type of computer environment required to run your program, and the other sets up the mapping between the files in your program and the files on the actual data sets. So it's the link between your program and the system it's running on. The data division sets up all the data that will be used within your program. That includes files, data from other programs, what type of storage or memory you'll use while the program is running, and what it will give up when the program ends. Then there's the procedure division. This is where all those sections and paragraphs go. So the instructions for how to take data in, how to set up the variables, performing math on them, interacting with the user, and all that kind of fun stuff, that happens in the procedure division. Are you ready to see all those statements, divisions, sentences, and paragraphs and actions? I sure hope so, because it's time for a lab, Basic COBOL Syntax. In this lab, you'll connect to an IBM Z system, check out a simple COBOL Hello World program, and then submit the JCL to compile the program and view the output. Good luck and have fun. In this section, we're going to talk all about COBOL variables. I'm pretty sure every programming language in existence has variables of some sort, and even basic algebra has the concept of having a letter represent a value, like x equals 5. COBOL is really no different, though it does put its own spin on some of the details, which we'll cover here. Simply put, a variable is a name chosen by the programmer to represent a value. That name is referred to as a data name. That data name can be anything as long as it's 30 characters or less, doesn't contain any spaces, is made up of only letters, digits, and/or hashes, and isn't a reserved word. So some examples of good data names might be balance, inventory 12345, and North American sales in 2020-final. That's exactly 30 characters. There would be no problem with any of those. However, if we wanted a data name of top 5% with a percent sign, or phone numbers with a space in the middle, those would not be good. We also have to think about what type of variable we want, because when we declare or create a variable, we have to tell COBOL what it's going to be. Numeric, just numbers, alphabetic, just letters, or both, alphanumeric. We also have to tell it just how many of those letters and or numbers we think we're going to be using. And we do all this because COBOL is an extremely efficient programming language, and part of what lets it be so efficient is knowing exactly what's going on with all of its data right from the beginning. We set this up in the picture clause. Picture, or pic for short, sets the length and the data type of a programmer-selected variable name. So pic9 is a single numeric value where the length is 1. The 9 means numeric. It doesn't mean it's a value of 9 or a length of 9. It just means here's a variable of numeric type, and since we didn't specify a length, we only get 1. It defaults to 1. So I don't know, maybe we're programming an elevator in a building with 9 floors. We could use that to store what floor we're currently on. Could be handy for that. And if we need more than one digit, we can specify that within the parentheses, like here, pic9 parentheses 4. That says it's a numeric variable, and there's 4 of them. That might be a good place to store perhaps the year, because obviously you would need 4 digits to represent a year, like 2020 or 2021 or 5545 or 1999. 4 digits for the year, always. Pic A means we have a single alphabetic character, and because we didn't specify length, we only get 1, so I could use that to store my favorite letter, Z. Pic X8 gives us 8 alphanumeric characters. X means alphanumeric, and with that many, I could store a US license plate made up of up to 8 letters and numbers. Now, not all pic clauses are created equal, so you need to know that the maximum length of a numeric picture clause is 18, while an alphabetic pic clause can be up to 255. And know that there are lots of other types of pic clauses. We will dive into those as we need them. For now, just focus on those 3: numeric, alphabetic, and alphanumeric. You can use picture clauses to represent symbols that appear in the value. So for example, pic9 parentheses 4 V99. What the heck does that mean? Well, 9 parentheses 4 means there's 4 digits. Then we've got a V, which represents the decimal position, the dot. Then 2 more 9s, so 2 more digits. We can use this pic clause to represent 1425.82. That could be a radio frequency or a measurement of some sort. We can also do something like this. Pic $9, 999 V99. That can be used to represent $1,234.56. The $ and comma carry through, and the V indicates the decimal area. When we think of a variable, we often think about something variable, meaning it can change. COBOL also has things called literals, which contain data that will not change during the course of the program. So I might use a literal to store something that I'm going to use several times in a program, but only want to have to set it once for all those other places. So maybe the name of a company, a string of characters that I use to separate lines in output, or copyright information. Anything that's going to get used more than once and isn't going to change while a program is running. COBOL has a few figurative literals built in to make things easier. You can use them without setting them up yourself, and a few you'll find most handy are 0 and zeros, space and spaces, low value, high value, null, nulls, and you'll notice that for some of these, there's a singular as well as a plural version. Very handy. So if you're starting a new variable and you want it to be all spaces, the efficient way to set that up is using the spaces literal, rather than sitting there and going space, 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 space. Using literals is what efficient programmers do, and I want you to be an efficient programmer. Up next, our good friend, the data division. All of the data you're going to use in your program gets set up in the data division. To add structure to this, we use what's called a data relationship. We can see that by looking at this segment of code right here. In this data division, we've got level indicators, each with their own descriptive entry. PrintRec has a level indicator of 01, meaning it's the highest, and then the data definitions are below it at 05. And the file account rec has its own set of variables with their own level indicators down here. Don't you just love that structure? It's basically saying the data this file needs are the account fields. And then below it, it spells out exactly what those account fields are. So we've declared the data. Let's do something with it. Move and compute are reserved words that we use to alter the value of variables. Move does, well, you probably figured it out, it moves the data from one place into a variable, and compute is used to perform math. So in this example, we've got a bunch of 77 level variables up top, which are who, where, why, rate, hours, and gross pay. You'll notice the first three are alphanumeric and the last three are numeric. Then down in the procedure division, we're using move to set up some of those variables. The who, where, and why are Captain COBOL, San Jose, California, and learn to be a COBOL expert. And that's spelled out pretty clearly on those lines. We're also setting the hours and rate to 19 and 23. We are not going to set the gross pay with a move. Instead, we're going to use compute and set that to the answer of hour times rate. And then lastly, we'll output the values of our variables with some text before them so the person using the program knows what value they're looking at. Pretty simple, right? Good, because it's, oh yeah, it's time for a lab. Take a look at the payroll 00 COBOL source code in the id.cbl dataset. And when you're ready to give it a try, make sure you're submitting the JCL for it and not the COBOL itself. You submit the JCL to run the COBOL. Got that? I know you do. Have fun. Up until now, we've mostly been moving data between variables, taking them from user input or outputting them to a display. Now we're going to take things to the next level and start working with files. To do this, we're going to use select and assign clauses in the environment division, FD statements in the data division, and from the procedure division, open, close, read into, and write from statements. The environment and data division is where we describe our inputs and outputs, which will get used in the procedure division because, as we all know, that's where the action happens. Let's take a look at that action in action. Here you can see the file control paragraph in the input-output section of the environment division. What we're doing here is associating each COBOL internal file name with an external dataset name. In this case, print line is the name of the internal file name, and PRTLINE is the external dataset or file. So that's the select and assign clauses in the environment division. Further down in the data division, this is where we define the level numbers, variable names, data types, and lengths. The FD reserve word is used to give the COBOL compiler more information about those internal file names. So print line, which is linked with the dataset file PRTLINE, has these fields, types, and lengths. And account rec, which is linked to ACCT-REC, has these fields, types, and lengths. When your COBOL code is running on an IBM Z mainframe, it'll have access to both traditional ZOS datasets as well as Unix files. For right now, we're going to focus on the ZOS sequential data storage method because it's extremely common and a good place to start when working with files in COBOL. A dataset in ZOS is made up of records, and you can think of each record as a line within a dataset with a defined length. So like anything written out row by row, you'll find the exact value you're looking for by scanning down to the right record and then across for the field you want. If you take all these fields and add up their length, that makes up the entirety of the length of that record. You got it? It's kind of simple. The way data input-output, or I/O, is handled is a program says, hey, I'd like to read this piece of data out here. And then the operating system or data I/O subsystem goes and gets it and places it into memory where the program can go and read it. If a program is requesting lots and lots of reads, one right after the other, that's a lot of I/O operations, which is somewhat inefficient and can lead to slow performance. It would be like going into a restaurant and ordering a soda, and then waiting until that's brought out and saying, you know what, I'd also like a hamburger. Then they bring that out and you say, fries too. And they bring that out and you say, ketchup. and then they throw you out of the restaurant because that's extremely inefficient and annoying. And we don't want to be inefficient or annoying. In COBOL programming, we have this concept of something called blocks. Because we know so much about the records, we can load data as a block, where a block is a group of records. As long as the program is going to read one record, followed by the next, and so on, we can get the records we want in order into what's called a buffer. Take a look at this. We can see a block of records loaded into a buffer where the overall record length is the size of each field combined. We set that overall block size in the buffer with the block contains clause. Earlier, we used the assign clause to describe a dataset source file. We said select account rec with a dash in it, assign to account rec. If we're running this in ZOS using JCL, we need to have a JCL DD statement to link account rec to that actual dataset. The JCL required for the COBOL compiler to make the connection back to the actual dataset looks something like this. / account rec dd dsn equals my.data, comma disp equals shr. If you're unfamiliar with JCL, this is a data declaration statement. That's what the DD stands for. It says that for account rec, look here at my.data. The disp equals shr just means that it expects that the data set exists before we try to use it, and that other people can use it at the same time. We don't require exclusive access. Now, I don't know about you, but I kind of want to see this all spelled out from end to end. So we'll start out with account rec. That's what we reference within our procedure division in the actual code. Account rec is what's defined in the environment division's input-output section. / account rec, ACCT-REC, 7 characters, then gets connected via a DD statement to my.data, the actual data set on the disk. Now, don't sweat the JCL stuff too much right now. I know you came here to learn COBOL, not JCL, and chances are if you're given some code to write or modify, somebody will prepare that JCL for you, or at least tell you what data sets and names to use, so you won't have to guess. There's a link to an online resource for basic JCL concepts in the course notes if you're curious though. One other important note, the COBOL compiler assumes that what you tell it for the file names is true and correct, and it will work when it goes to run because it doesn't have any way of checking what's actually in your JCL or actually on the file system. And if any part of that chain is broken or not correctly linked, you're going to get an error at runtime. That's why it's important to have a good naming scheme because chasing those types of errors is no fun at all. Up next, we'll talk about putting all that to use in the procedure division. Now we're in the procedure division where we actually open those files. That happens in the open files section, and we can open files for input and output like this. Here we've got account rec open for input and print line open for output. And just as we open the file, we should really make sure to close them when we're done. This can be done at the program completion, or if it's going to be a long-running program, when we're done using that file resource. We do that with the close-stop. So we just say close account-rec, and then close print-line, and then stop run stops the processing. Because COBOL is often used to handle lots and lots of data, it's a safe assumption that we'll need a way to process records one after the other until we're done. You may have seen in other programming languages the concept of a for or a do statement. COBOL uses perform, and in practice, it looks like this. I encourage you to hit the pause button on this screen and study it for a little bit, because while it's extremely straightforward, there are a few bits in here that might raise an eyebrow, and we'll go through all of that. So I'm stalling here to give you time to find the pause button, and we're back. So starting at the top, we've got the read next record paragraph. The first thing we're going to do here is perform a read record. That's the first line. There are no conditions about it. We're going to do a read record at least once. That read-record is defined down here. That is going to read the next record from the file, and if we're at the end, put a Y, presumably for yes, into last rec. Then when we're done reading, we have this end read. And even though that terminates logically and explicitly with the end read, it also terminates implicitly with that period there. So we're just being complete, covering all of our bases. Now, going back up into the read next record, we're indenting. And our first line here is a perform until. It says perform until last rec equals y. And why would last rec equals y? It would be y if read record detected it had hit the bottom and had processed its last record. And if that file was empty, it would hit this first perform, put a y into last rec, and then the logic of this until statement would say we're done performing. We're bumped out of the logic because there's nothing left to do here, and we've also hit this implicit terminator, so we're done with this paragraph if the file is empty. If the file has a couple of records in it, like we would expect, then we continue, and we're going to do a write record with the data we just got. That's defined down at the bottom of the example code. Then we'll do another read record before going back up to the top of this perform loop, where we'll check to see if we got a y. If it does, we'll end. If it's values, then we're going to use write record to write them out, continuing that process until we've hit the bottom of the file, setting last rec to y, and finishing. Reading a file from top to bottom is like the C major scale of COBOL programming. You're going to have to do a lot of it, so you should know how to do it forwards and backwards. And this code right here is a great example of this type of logic done right. Keep all that good stuff in mind as we go into lab number 3. You'll use everything we touched on in this lesson to fix some code. Remember that the all-important chain of links between the procedure variables, environment variables, and the JCL datasets needs to be correct. And if it helps, write them out so you can double-check things as you write it. Go get to it, lab number 3. You'll often hear COBOL referred to as a structured programming language. In this definition, structured means that it relies on the concept of passing control and adhering to a flow structure as a program executes. In other words, the way that you write your code is used to spell out how it should be executed. People writing code in C, PLI, Python, and of course COBOL use the structure of their languages to ensure code flows exactly the way it ought to. Another style of programming, known as object-oriented programming, divides code up into smaller segments called classes, each having its own specific purpose. And each class has its own set of variables and methods. Then, once the classes are defined, you write the code that describes the interaction between them all. And if you're writing a program where you're going to benefit from this type of class-object relationship, it allows for you to write very capable code without needing to define each and every instance of each and every class from scratch every single time. However, I can tell you from a little bit of experience that it's also very easy to write something that looks very simple but behaves completely different from what you intended. You're essentially building the structure of code on the fly, and that has its advantages, but a lot of the code people write on COBOL needs to be transparent and readable and easily diagnosed, which is a lot easier to do in a structured language. You get the ability to jump around a little bit in COBOL, but you should be sure to use those sparingly and not rely on them to provide the backbone of your program. As we saw before, COBOL passes control primarily using the perform keyword and using paragraphs. So how can we best make use of this structure? I'm so glad you asked. Let's take a look at basic program control and flow through a snippet of code. We're setting up the output of print line. We're setting the message headers of print rec to the number is. And then we're adding 1 to the counter variable, moving that value to message to write, and then writing print rec, which will print something like the number is 1. Then we do the same thing again with the exact same code, adding 1, moving it to message to write, and printing it for as many times as we feel like repeating in this section here. The only indication I have that I might be done is that the name of the program is 210.1, so I can assume we'll do this 10 times. A simple looking program, but dreadfully repetitive and not a very good use of anybody's time. Remember, we want to be efficient, and that doesn't look efficient. Those 3 lines of code keep getting written again and again and again. So rather than typing them out, let's address that issue right here. We'll move those 3 lines of code into a new paragraph called write new record. And then we'll just call that paragraph 10 times using the perform keyword. So the program will get here, then run this, then go here, then run this, and it will do that 10 times. This is called an out-of-line perform statement because it requires jumping down here and then back up. And it's definitely less code, but it still seems kind of repetitive, right? That's where we need to look into using a loop, using an inline perform statement. And once I pop that up on the screen, you'll see exactly what I mean. In the previous versions, the part of the code we were repeating was add 1 to the counter, move that counter value to message to write, and then writing it out. Here we see the move counter statement. That looks the same, and here's that print rec. We wrap those 2 lines in this perform and end perform, which forms our loop. So what about incrementing the content of counter? That happens as a condition of the loop itself. Perform, that sets up the loop, varying counter from 0, 1 by 1 until counter equals 11. That, I mean, we really don't have to spell out what it does, right? It basically looks like English. Perform a loop where each iteration of the loop increases the counter by 1, starting from 1 until we get to 11. Why did we say 11? We had to say 11 because if we said 10, we would hit 10 after incrementing it, match this until clause, and bump out before executing the move and print part. You'll see logic like this in other languages, like this Java example. Obviously, the COBOL version involves a lot more typing, but it's easier to read, and you'll also get autocomplete, so your editor will write a lot of that for you. Another way you can get around this is by using a goto. Now, here's the thing about goto. Don't use goto unless you absolutely have to do it and you absolutely know exactly what it's going to do. Goto does exactly what it sounds like. It jumps the program to where you're directing it, and it just kind of picks up and runs from there. The difference between goto and perform is that instead of it being a special assignment that it will do and then return from, it's just going to go there and start executing from there. It's like when you're reading something online and you see a word or a phrase you don't understand, so you search for it and you find a video about it and you watch that video. Ideally, you go, okay, cool, now I understand that, and you jump back to where you were. Or if you're like me, you go, hey, that was kind of cool. What was I looking at again? And there goes the whole afternoon. If you were to go back to that program we showed earlier and replace the second perform write new record call with a go to write new record like this, the program would jump ahead to the write new record paragraph, execute it, and then just keep on going because it didn't know that it was on a special assignment. It just thought, okay, well, this is where I am now. Just understand the difference and be careful when using go-to statements because you might be losing some of that structure that your program needs to be successful. If that didn't make sense, you might want to rewatch this video and check your notes because right now, we're going to go to the next video. When you start planning a program, start thinking in paragraphs. If you were to start whiteboarding the overall flow of a program, drawing words in boxes and connecting those boxes with arrows, a lot of those boxes will get implemented as paragraphs, and that's good. That's kind of the point. A paragraph gets defined in the procedure division, starts at column 8, and can have any name you like apart from a reserved COBOL keyword. The declaration of a paragraph is terminated with a period. The paragraph itself can contain one to many COBOL sentences and is terminated by either the start of another paragraph or the end of the entire program. From an application architecture perspective, you really want to spend some time up front charting out the flow of your program and deciding what part will get handled in what paragraph. If you start this way, instead of kind of figuring it out as you go along, not only will your code be less error-prone, you'll have a nice reference to use later on. Now, there are two big situations where a light should go on over your head and you'll say to yourself, ah, that's a good use for a paragraph. The first is if you find yourself typing the same couple of lines over and over and over again, like adding a bunch of numbers together and finding the average. If you find yourself doing that, think about packaging those up into a paragraph and giving it a name. And by the way, put at least a few seconds of thought into your paragraph names. Nobody wants to open up a bunch of source code to find paragraphs called do file stuff or test123. Aim for something like open input files or check for duplicates. That way you know exactly what's going on in there. Also, if you've got a couple of lines that need to happen a bunch of times, extracting those lines into a paragraph and using a perform keyword to execute them a certain number of times or until a certain condition is met is good practice for writing comprehensive code. A paragraph can come before or after the code calling it, but you should try to order your paragraphs close to the order that they will be executed in at runtime, just to make it easier to find them. What I'm saying is, don't just throw new paragraphs at the bottom of the program. You may see people start their paragraphs with numbers, and each paragraph will look like 1000-open files, 2000-read next record, and so on. Then, as you extend your program, you can add them into the appropriate significant digit. That way you can say, you know what, that paragraph should be in the 3000s, and so on. We kind of don't have to rely on this anymore with modern editors that can quickly jump between the paragraphs of a program, but this explains why you might see this done in code that you're looking at, and you may or may not choose to do the same when you write yours. You may also see empty paragraphs at the end of other paragraphs, like this. The open files end paragraph has no code and does nothing. But for someone reading through code, it makes a nice visual indicator that the code for this paragraph ends here. It also comes into play if you're using the perform through keyword, which we'll learn about in just a little bit. One of the simplest ways of setting up a loop is with times. For example, here we say perform 10 times and then some code, finishing with end perform. And we can set that up with a number, just like that, or with a numeric variable, like this. Perform my new paragraph counter times. Whatever counter is, it'll perform that paragraph that many times. We can also perform through, and this can be spelled out through or just thru. Check out this example. We have our first paragraph, 1000 paragraph A, that says perform 2000 paragraph B through 3000 paragraph C. This is another reason to consider the order that you state your paragraphs. Now, we'll hit this perform through, jump down and execute paragraphs B and C, and then finish this paragraph. We'll never hit D because we were only performing through paragraph C. We can also perform until, which will evaluate the check, and if that condition is not met, it'll take some action. This is usually done until a number hits a certain level or two variables are the same, like increment this value until it's equal to that value. In this example, the order is that we do the check and then do the code. And if the condition is met, we're done. We've done it until. If that doesn't match your logic, we can also do perform until with test after, like here. This will run the loop and then do the test. There's also perform varying, where we say something like perform varying counter from 0, 1 by 1 until counter equals 11. We just looked at that earlier. And if you really want to get fancy, you can nest those performs like this, where we've got two counters going on, counter and counter 2. And every time we increment counter by 1, we're going to step counter 2 from 1 to 5 in increments of 1. So we would get 1, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 3, 1, 2, 3, 4, 5, and so on. Now, I don't know about you, but I'm starting to get a little loopy myself. In the next video, we'll cover linking in other COBOL programs. A COBOL program can call other COBOL programs, and you do that with the call keyword followed by the name of the program. That can be call prog A1 with the literal program name being in single quotes, or like this, where we move the program name to a variable and then call that variable. The way a calling program calls a called program is through something called linkage, and I'm going to show you a very basic example of it. The program being called has this section called the linkage section, and in here it defines three variables, month, day, and year. They're all numeric, 2 digits for month and day, and 4 for year. Of course there's 4 for year. And they've all got an ls at the end, so you know they're in the linkage section, as opposed to the variables up here in the working storage section, which have a ws at the end. So this program over here that we're calling, it knows that it's going to be called, and it prepares itself by setting up the linkage section. It also sets up the procedure division using the using keyword, so it's going to use those 3 variables from the linkage section in addition to the 3 variables from the data division working storage section. Now, the calling program sets up those 3 variables in preparation for this, which in this case match the variables in the linkage section. We want to set those up just like any other variable. Then we do this: call date sub using month out, day out, year out. There's those 3 variables. We're calling that other program and giving it those 3 variables to store the output that it generates. Linking programs can get quite complicated, but for now we're just going to leave it at that. Just know that there are ways of passing actual data as opposed to references to data, mechanisms for getting a return value from a called program, and all other sorts of goodies. Once a program reaches a certain size, you're almost guaranteed to see everything we've talked about in these last few videos put to use. So if this all makes sense, you're in good shape. Let's keep this party going. A big part of COBOL is generating reports. You've got tons and tons and tons of data, and you need a way to produce a report of that data so someone else can look at it and go, yes, that's very good, yes. For that reason, we've spelled out an example of generating report data here, which can be very easily scaled out to handle multiple records and called any number of different ways. At the end, you'll be asked to complete a lab that puts all of this to use. Previously, we looked at the select and respective assign programmer-chosen names. We had something like this in the environment division. We used printline as the internal COBOL file name for the output. Now, in the file descriptor, marked by FD within the file control paragraph, we start to connect it all together. The FD entry defines the layout of the record within that print line internal file. And you can see we're saying FD is a file. The highest level descriptor is printrec. And then within that printrec, we have the individual fields defined. First, account number O, presumably for output, that's a value of 8 alphanumeric characters. Then look at this, filler. That's an odd name for a field, and it's actually not a field, but a COBOL reserved word. Remember those? We use filler to allocate memory space, typically between words or variables. And filler can be empty, it can be dashes, or any literal. In this example, it's 8 characters of account number, then 2 spaces. And you can see that we spelled out spaces there with S-P-A-C-E-S. That's a handy shortcut so you don't actually have to type out the spaces. Each one of those filler lines in here is just inserting 2 empty spaces. And in this case, it might seem somewhat basic, but without filler, your reports would just be a bunch of values slammed up against one another. Consider this partial program. This is the working storage section. We've got 4 headers defined. There's no logic in here. This is just something that defines what our data looks like. Notice we've got some areas up here that are just filler, and we're filling them up with this text, Financial Report 4. Then in header 2, it's a mixture of literal labels and printed out variables. So we'll have the word year. Notice it's year with a space at the end of it. That's why it's 5 characters. Then the value of HDR, year, header year. Same with month and day. Header 3 is all filler. It's just account, 2 spaces, last name, 2 spaces, limit, 2 spaces, and balance, and then 40 spaces. If you need 40 spaces for your account balance, I want to be your friend. Send me an email once you're done learning COBOL. Then in header 4, this is more filler. It's 8 dashes, 2 spaces, 10 dashes, 2 spaces, and so on. So what I see up here so far is a header that goes up top and that says what the report is. And then there's some sort of header info that spells out the time period the report is for, which is kind of important. And then we got 2 headers for the values, which I'm assuming will be listed out below. Makes sense so far. So that header 2, that's date info. The data name layout for the date info is defined here. And it's kind of neat how this works. The high-level variable name is WS current date data. That's WS for working storage. And then within that, we've got 2 sections, WS current date and WS current time. The date is divided up into the year, month, and day, and the time is divided up into hours, minutes, seconds, and milliseconds. Now we know exactly what that current date data looks like. Which is good because that's one of the first things we're going to do in the procedure division, aka the division where all the action happens. Check out this procedure division. We start out with a paragraph called write headers, and then we've got these 4 move sentences. The first one takes the current date from what's known as an intrinsic function. More on that later. But what it does is it takes the current date of when that code is actually executed and it copies it into WS current date data. Then, because we defined how the fields of year, month, and day line up within that data name layout, we can just tell it to move the year, month, and day portions of that data into those 3 variables. Then in lines 5 and 6, we write out our report header, that's the financial report 4 part, and the date info that follows it from header 2. We're writing those out to print rec, and we're writing them out there from header 1 and header 2. Then we move spaces to print rec in line 7. If we didn't do this, we might leave stray characters behind. We want to start out with the next series of moves and writes assuming that we have a blank record, and then we write it out. So if you're following along at home, which I hope you are, we've got the financial report 4, then the date header and info, then a blank space because in line 8 we wrote out that line of spaces and put it into the print rec in line 7. Lines 9 and 10 write out the column headers of account, last name, limit, balance, and those nifty dashes that went under them. Now all we have to do is print out the data that goes underneath those headers, and you know what? That's where the lab comes in. That will show you how you can take data from a file and use it to generate a report with all the nice formatting and spacing that makes it nice and easy to read. After that, why don't you report back here for the next lesson? The path that a program takes is sometimes referred to as its logic. Does the user want to enter more data? If yes, then we'll jump to the part of our code where we'll let them put in more data. If they're done, then we'll jump to the part of our code where we're going to process that data. It's kind of like hitting a fork in the road, and we use what we know to inform that decision. Maybe you want to look at a bunch of accounts and find the ones that haven't been updated in the last 60 days. In that case, we're taking the difference between the most recent update and today's date and comparing that difference to 60. Presumably, if the difference is greater than 60, then we're going to do something special with that account. That's all logic, and unless we insert our own logic, a program is going to run from the top to the bottom until it's done. So we need to learn how to express what we want to happen in a program's logic. 3 of the most common types of COBOL conditional expressions are general relation conditions, class conditions, and sign conditions. And a lot of these are fairly simple. It's taking 2 operands, comparing them to one another, and saying, is this greater than that? Or is this equal to that? Or saying, is this numeric? Is this lowercase? Sometimes, because of the way our logic is structured, we'll want to say, is this not numeric? Because maybe we asked the user for a number and we got back something like XX. And we need a way of saying, if this is not numeric, go and prompt that user again and remind them we're looking for a numeric answer. So whenever you're writing a conditional expression, they typically start out with is. And then there's a test or a comparison afterwards. And you can, between the test and the comparison, throw in a not to flip that logic around. There's another important and powerful tool you have in writing program logic known as conditional names. These are used primarily to say the input we're taking needs to pass this test. A conditional name is declared in the working storage section with an 88 level number. In this case, it has to be an 88 level number. We use a conditional name to say the variable that I'm under needs to match this, and it can be a literal, a series of literals, or a pattern, or anything like that. And it's a good way of verifying user input, and again, it always has to be an 88. Take a look at this example. We move AZ into USA-state. Then we enter this if statement, if state. The only way this will pass as true is if state evaluates as true, which in this case will only pass if it's equal to TX. So we're going to say the state is not Texas. Then here we're moving TX to USA-state. That will pass because it matches that 88 conditional statement. It equals TX. Why would we do something like this? Well, imagine instead of just putting in one state, we put in all 50. That would make sure somebody didn't put in something like ZZ or 1, 2 as their state or something like that that didn't make any sense. So we can use conditional names as a way of validating or limiting data before we try and do something with it. There are other ways of implementing this type of logic, but being able to have one place to define the scope of the data for a test is quite handy. If we're comparing values like if this is greater than that, we use conditional operators, and those include is greater than, which can be written out as is greater than sign. Remember those alligator mouths. Or is equal to, which can be written out with the equals sign. We can also say is greater than or equal to with is greater than equal to. We can take that concept and put it to use in conditional expressions. That's where we put those if, then, else statements to use. And you're probably already familiar with those concepts, either from another programming language or just from everyday talking logic. If it's nice out, then I'm going to go for a hike. Else, I'm just going to stay inside and play video games again. We've defined two possible outcomes and what will inform that decision, the weather. In code, we might write something like this. If facial expression is happy, then say, hey, I'm glad you're happy. Otherwise, say, what can I do to make you happy? Obviously, we would want this program to actually do stuff if you're happy or not happy, maybe clap your hands. But this shows a basic if, then, else statement. We have another way of doing this that's more useful if there's more than two paths, and that's an evaluate statement. We set that up like this. First, we evaluate facial expression. When it's happy, we do this. When it's sad, we do this. When it's perplexed, we do this. And we can keep on going until we run out of possibilities. And then we hit the end where we just say end evaluate. This comes in handy for menu type items, like press 1 to show account balance, press 2 to make a withdrawal, press 3 to transfer money, etc. Each one of those could be a when in this big evaluate statement. Another thing that happens quite often in programming is performing some sort of function or a set of steps until something happens. Maybe it's processing files until we've reached the end, or adding stops to this truck driver's route until the truck is full. If we're iterating over data, specifically tables, trying to find a specific entry, we can use search statements. That syntax looks like this. Search the facial expression table until you've found the index marked happy. Then presumably we do something with that record, although in this example we issue a stop run, so I guess they found happiness and there's nothing left to do. Let's get back to those conditions. You know we can say if this number is equal to that number. That's a test of the relationship between two operands, which can be numeric or text. We can also use conditions to test the content of a data item, like is numeric or is not alphabetic lower, or even is kanji. And for numbers, we can say is positive, is negative, and is 0. And just so you know, we're really only skimming the surface here. To read more about all these conditions, visit the IBM Knowledge Center for Enterprise COBOL. There's links for that in your material. We're coming up on that time to put what you've learned to use in a lab, and we're still working on those reports. This time, we're going to add in a special case if we happen to be in the state of Virginia, which will result in a special entry in the last line of your report. Good luck, and I'll see you back here when you're done. COBOL is often used to process lots and lots and lots and lots of data. And a lot of data is made up of lots and lots and lots and lots of numbers. So in order to deal with all of those numbers, we need to take a look at COBOL Arithmetic Expressions. That's it. That's the intro. Nope. More? All right, let's put this graphics budget to use. It's math time. Nice. Good job, guys. So, what is arithmetic expression? Well, an arithmetic expression can be built up with numbers, variables that represent numbers, the figurative constant of 0, and any combination of those enclosed within parentheses, including any combination of all that I just mentioned, having mathematical operations performed on them. I think that about covers it. For example, number of people minus number of staff times 3 divided by 8 would be how many pizzas you need in order to feed a crowd of this many people, assuming we're not feeding the staff. Each person will want 3 slices, and there are 8 slices per pizza. That's a pretty good mix of variables and literals and parentheses. And we can spell expressions out with plus, minus, times, divided by, and you can also use 2 asterisks or stars to show exponentiation. So 2 star star 8 is 2 to the 8th power, meaning we keep doubling 2 8 times. That's 2, 4, 8, 16, 32, 64, 128, 256. 2 to the 8th equals 256. Sometimes it makes sense to spell out our arithmetic expressions using the compute command. This can help make your code more readable or just focus a series of arithmetic operations in one place. So we can say compute z equals a plus b divided by c exponent d minus e. We can also say compute xyz equals all of that, and it will assign the answer of whatever that might be to all 3 variables, x, y, and z. Now, you've probably heard of the order of operations before, and if a part of your brain lit up that you haven't heard from in a while, the word PEMDAS probably does the same. That is the order in which we tackle an expression, starting with parentheses, then exponents, multiplication, division, addition, and subtraction. PEMDAS. By default, COBOL will evaluate expressions this way. If you want to either circumvent that order or you want to make it more clear for yourself or others who are reading your code, you can also enclose sections of your expressions in parentheses. COBOL will start with the most nested part of the expression, the part enclosed in the most parentheses, and then keep working its way out. After that, it'll look at the unary operators, positive, negative, then exponents, then multiplication and division from left to right, and then addition and subtraction from left to right. That means that an arithmetic expression must begin with either a left parenthesis, a unary operator, or an operand in the form of a literal number or a variable representing a number. There are limitations to how far you can push arithmetic expressions in COBOL. The first is that exponents in fixed point expressions cannot be more than 9 digits. If the compiler sees this, it'll truncate it and you will get a diagnostic message. Also, while the data descriptions of operands in expressions don't need to be the same, meaning you can multiply a 2-digit number by a 4-digit number, the maximum size of each operand is either 18 or 19 decimal digits, depending on the compiler option used. If you're working with data that requires either very big numbers or a very high degree of precision, make sure you know if you're using compatibility or extended mode for arithmetic. There are also considerations to consider when dealing with the rounding of data, and there's more to get into that we can't cover in its entirety here, but that's all spelled out in the Procedure Division Statements COBOL language reference. As you have probably guessed, we're going to get to use some of these new skills in the upcoming lab. Check out this change to the working storage section. Here we've got t-limit and t-balance. There's some big numbers in there, and we'll learn more about data types in the upcoming data type section. But I can tell you right now, those are big numbers, or at least able to represent big numbers. They're a comp3 data type, and they start out with a value of 0. And look at this, we've got what looks like more header type content, except we're calling it trailer. And I'm not a betting man, but I think that's going to come at the end. It looks like it's showing us some sort of totals, so that makes sense too. And then in the read next record paragraph, we now have a perform limit balance total line, which is calling this, which is two compute statements which look like they're keeping a running total of the balance and total from every line it's processing. Of course we're going to write it out. So we've got this write t-limit t-balance paragraph, which moves the running totals into the -o variable so that when we write the trailer lines out, the actual values are going to show up in there. Those are the parts you'll need to finish this section's lab. And by my calculations, it's time to get to work. Computers don't have fingers. I mean, do they? I mean, I guess. No, they don't. Except what about? No. Computers do not have fingers. Let's just stick with that. So when a computer is thinking of a number, like the number 8, it's not going like this. It's lighting up little bits of memory that represent that number 8. It's got its own methods of taking numbers, letters, and other concepts and representing them electronically. One of the ways you can make sure your programs are running as quickly and efficiently as possible is by choosing the best way for COBOL to represent that data in its memory. Let's start out with numerical representation. There are 5 different computational value representations. Let's start with Comp1. Comp1 is also known as a single precision floating point number representation. This is useful for numbers that are very small and close to 0 or very large, up to 10 to the power of 38. However, Comp1 has somewhat limited precision. It only has about 7 significant decimal digits. Anything beyond that gets rounded, so a value like $1,234,567.89, that right there is 9 digits, and it's going to get rounded, which if you're dealing with dollars and cents, you might not want to happen. But for simple numbers, a Comp1 might work. Then there's Comp2. This is a double precision floating point numeric representation, and this can handle bigger numbers, about 10 to the power of 307. It has more significant digits, up to about 15, so it goes further than Comp1 in all regards, but it is still somewhat limited. And then there's, can you guess? We did Comp1, Comp2. Yes, you in the back. No, it's actually Comp3. Comp3. And this is where it gets interesting. This is what's known as a BCD, or binary coded decimal. This is by far the most utilized numeric value representation in COBOL. It is also somewhat unique and native to the mainframe computer and Z architecture, and with good reason. It has to do with decimal fractions. When you do lots and lots of operations with decimal fractions and the data is stored in binary, that's when you start to get rounding issues. Representing that data in binary coded decimal avoids these issues. It exactly represents values with decimal places and can go up to 31 decimal digits. Ask someone in a banking, credit card, or payment processing industry why they depend on COBOL, and they're probably going to mention BCD, binary coded decimal, and decimal fractions. And then there's Comp4. Comp4 is only capable of representing integers. So if you're dealing with something like a counter, or you're only working in integers, using Comp4 has you covered there. And then there's Comp5, which is the same as Comp4, but with it you can specify the position of a decimal point. It's got space efficiency of Comp4 with the exactness of Comp3. The drawback there is that it cannot exceed 18 decimal digits. So there's your numerical value representations. Numbers are good, but sometimes you want to use letters, and you'll be happy to know that COBOL's got you covered there as well. There's EBCDEC, which stands for Extended Binary Coded Decimal Interchange Code, and ASCII, which stands for American Standard Code for Information Interchange. And it's not like one supports bigger words than the other. It really just comes down to how the characters are represented in the computer's memory. EBCDEC has 8 bits per character, ASCII uses 7, and the characters are distributed across the possible combinations of those bits differently. Today, the only place you're likely to see EBCDEC code is if you're on an IBM mainframe. Most everywhere else uses ASCII or Unicode. However, just keep this in mind if you're working on programs written a long time ago, because every once in a while you'll go to load some data and it will show up looking all weird. Your first instinct should be to say, is it possible that this data is EBCDEC and I'm trying to load it in ASCII, or vice versa? Because that happens quite often, and now you'll know and you'll be prepared. In this lab, you'll deal with an issue just like that, where, spoiler alert, there's a mismatch between external data and the COBOL representation of that data. There's a hint and an explanation in there to help you along, because this is a tricky one. If you're like me, one of the things you like about COBOL is how straightforward each line of code within a program is. It does what it says it's going to do, and there's really no mystery about what "do this until this happens" means. However, sometimes you need to do something beyond just add two numbers together or print out a line of text. And it would be a shame if every time you needed to, for example, turn a string of characters from lowercase to uppercase, you had to go and build that paragraph of logic all by yourself. First off, you're just repeating work, and more importantly, that's important code logic that needs to work right every single time, being added onto whatever the primary role of the program that you're writing is. There's got to be a better way. Well, fortunately, COBOL has a number of what are called intrinsic functions built in that you can use. And if you're working with business data, chances are there's something in there for you. Don't worry, it's not like there's 500 new functions you have to keep track of. The most recent release of Enterprise COBOL for ZOS includes 70 intrinsic functions, and they fall into the categories of math, statistics, date time, financial, character handling, and general. Let's take a look at some of those intrinsic functions. They all follow the format of function, then the name of the function, and then any arguments passed to that function in parentheses. For example, look at this. We've got two variables, item 1 and item 2. Item 1 has hello world in it with a capital H and a capital W, the rest lowercase. And then there's item 2, which is empty. And we're going to display item 1, which should look exactly like it does up here with that capital H and capital W. Then we're using the uppercase and lowercase intrinsic functions to show item 1 in both uppercase and lowercase form. Note that this is just being called in the display function, so it's not altering the stored data. That's just how it's going to show up when the display goes to show it. Then in this line, we're moving the uppercase version of item 1 into item 2 and then displaying it. So in this last line, if we display item 2, it'll show hello world in all caps. That's going to come in handy in making sure we don't have any duplicate values. Otherwise, First Street with lowercase st would be a different entry than First Street with an uppercase st, which happens quite often. If we just uppercase everything, we can be sure that all the data coming in is case insensitive. There's also math intrinsic functions. Got a bunch of values that you want summed up? You could line them all up and make an equation out of it, or you could say compute x equals function sum a, b, c divided by d. That'll assign x the value of a plus b plus c divided by d. And just like before, anything within a pair of parentheses as seen as one operand, and it needs to get figured out before totaling the sum. But wait, there's more. What about dates and times? I mean, come on, man. COBOL's got you covered. Check out this code. We've got a variable called YYYYMMDD, length of 8, gonna be filled with numbers. And another one called integer form. That one's signed with 9 spaces. We can use the function of current date with the argument of 1:8 and move that into the first variable. What's going on there? Well, we're specifying the output. In this case, we want the output from character 1, that's the 1, through 8, that's the 8, which just happens to be where the year, month, and day live within that output. Then we want another function, integer of date, to turn that date into a number. That number is the number of days that have passed since January 1st, 1601. So it's going to be a big number, but it's also not likely you'll need to go back much further than 1601, so pretty safe bet. Anyway, what we have now is essentially a count of days. With that, we can add 90 to it, and now we're talking about a date that's 90 days from now. You see what we're doing? Now we're going to use another function to transform that integer form back into year, month, and day form using the date of integer function. See what we're doing there? We flipped it. And now we wind up with what is a nicely formatted date in the form of year, month, day. And that's 90 days into the future because we added 90 to it. And that takes into account going through all the months of different lengths, leap years, and all that stuff. Intrinsic functions. And there's more, lots more, like 60 something more. Keep that in mind as you're writing code and you think to yourself, gee, I can't believe I have to write this out by hand. Because there just might be an intrinsic function that you can use right there. Intrinsic functions sound like something you might want to try? Oh, well, guess what? Act now and you can do just that with this Intrinsic Functions lab. Get yours today. We are at the last section of this COBOL series. First off, I'm extremely glad you made it here, and I hope you feel a lot more confident in your own abilities as a COBOL programmer. Of course, the world goes on from here. There are lots more functions, methods, and ways of dealing with files and input to explore, but if you made it this far, you can tackle anything else you come across. You'll be able to understand the syntax, plug it into your code, make requested changes, port a program from one system to another. You've got all that. Just like with any other programming language, the internet is full of code samples, mini exercises, and forums with people looking to help. Go to the Open Mainframe project and go into the COBOL section on there for a good head start on those resources. Whether COBOL is your first programming language or your 15th or your 50th, I hope you've learned what this specialized language is all about, and you'll see why it's used so widely in highly transactional systems all around the world. From our team to you, thank you for watching, thank you for participating, and we wish you the best in all that you do. Stop, run.